Hello everybody, my name is Jeff Bees and I'm here to talk to you about Lab 2 for the ME4031W course. So just a quick walkthrough of the objectives. This experiment actually can be broken up into 3 parts. Each of these parts I will break up into 3 subcategories dedicated to setup, equipment procedure, and deliverables. So we'll start out with the setup for part 1. Here's a simplified image of what you will see when you get into lab for the setup for part 1. Now we'll clean this up a little bit. And here we have a schematic. Some notes about this is that we will start out using the oscilloscope just to make sure that the function generator is at the proper voltage and frequency. And then we will actually remove that connection and then connect the function generator directly to the DAC, which will then send the information into the computer with LabVIEW, and then it will output sound from the speaker. So we'll start out talking about the function generator. First, you're going to want to specify the function type as a sine wave, and then these extra functions, you actually want to set them all to off, which means that the button is out rather than in. And then for the range actually specifies what range of frequencies are available to the function generator. So since we're going to be dealing with a signal of 1 kilohertz, you'll want to select 5 kilohertz range and then use the coarse and fine frequency knobs to make larger or smaller tunings towards that 1 kilohertz signal. One of the downsides to the function generator is it doesn't tell you what the amplitude of the signal is, and so you'll use the output level knob to adjust this, but you'll need the oscilloscope to reference that, and you'll want to plug into this output port in order to send that signal to the oscilloscope. Once you're working with the oscilloscope, to start out, the first step that you'll want to go with is pressing the auto button. This is basically a search function where the oscilloscope determines what the best time span and amplitude span to scale to in order to properly view your signal. It doesn't always work, but for a clean sine wave like we'll be generating here, it'll work pretty well. And then you'll want to actually click on this measure button, which will open up some options on the screen here, and there may already be options down below, in which case you'll want to click on the clear button and then press the blue button that lines up with the word voltage on the menu display that shows up on the right side of the screen. Once you've clicked on that, the scroll knob, you can actually twist this knob to scroll down to the options you want, and you'll scroll down to voltage peak to peak. And then in order to select that option, you will actually press down on the scroll knob. And then you will want to do the same thing, but select the average voltage. And a quick note about this is that you'll be measuring the average voltage because it won't be exactly 0. There will always be a little bit of an offset, and you want to note what that offset is. Because when you convert over to an FFT or a DFT, this DC offset comes as a 0 hertz signal. Then once you've got these 2 options showing up, you'll want to click this menu on-off button, which will remove this side menu away so you can just look at the 2 readouts that show up down below. And you'll then adjust the function generator's output level until you read a V peak to peak of 5 volts. You may end up wanting to resize the screen by either changing the vertical or the horizontal scale in order to maximize how much amplitude is being shown, and then having roughly 3 to 5 periods present. This allows the oscilloscope to measure more optimally because it measures specifically based upon what you see on the screen. So if this sine wave actually goes outside of the screen, you'll get an invalid amplitude reading. On the other end, if you have a really small scale, then your resolution will be really poor. So make sure that you can view as much as possible without getting invalid readings. Now, a word of caution to using an oscilloscope is they are rather complicated. They have a lot of options at your disposal, and it's really easy to get lost. So try to keep it simple and not mess around with the buttons too terribly much. The DAC that we're using is a USB 6210. The important thing is that it can sample at a maximum of 250,000 samples per second, which makes it very ideal for measuring sound waves, or in our case, voltage waveform signals. Now, the program that you'll be using will also output the sound that the software thinks it is receiving. Now, that isn't always the true signal, and in order to determine what signal you can expect, you want to use the Nyquist criterion as well as the equations for leakage as well as aliasing. And when you're operating it, make sure it's turned on to a low volume because the sound certainly adds up. Now, for the LabVIEW program, I'm going to play the video and kind of walk through these steps. So here we want to start out by making sure we've got the correct physical channel, set the device to the proper one. In this case, you'll only have one present, and set it to AIO. Then the terminal configuration should be set to differential. Number of samples we want to keep at 1024. And then the sampling frequency, you should start out with 32,000 hertz, which you can just type in 32K and it recognizes that. Once you've got all this set up, you can click Run, and it'll take a signal in. And this is the amplitude versus time signal. But if you want to go to FFT, just click on the tab, and you'll see now that the x-axis is frequency in hertz. And we've got a nice peak at almost 2.5, which is about what we would expect with 5-volt peak-to-peak. And we can activate a cursor, and you'll see that you can get a measurement down here of the frequency as well as the amplitude. And then you can check neighboring frequencies in order to determine the change in frequency between the different bins. And this will act as your resolution of frequency, and therefore a contributor to uncertainty. Another way you can do this is you can actually export the data into a spreadsheet, and this will output exactly what you see on the plot. And so if I were to actually plot this, we can see that it will look basically like what you got from the LabVIEW program. And so this can be a quick way to gather your information so you can kind of cruise through testing the different sampling frequencies. And then the information that you'll want to gather from this is the measured amplitude, which is where that peak is, the F measured, which is the frequency where that peak occurs, the maximum frequency, which is the 16,000 over here, and then the DF, which is the bin width, or the spacing in frequencies, which in this case would be 31.25, which we can see right here. Some things that I couldn't show you on here is that when you press Run, there will be an audible tone generated from the speakers. Keep a note of that, because when you start out with 32,000 hertz, it will be replicating the true signal because you'll be past the Nyquist criterion. But as you move down into less ideal signals, which is why you should start from the high value and work your way on down, you'll notice it change into something that isn't the genuine signal. Another note is that when you push Run to start with, you don't want to push Stop until you're done with the whole lab. Because if you press Stop, then it'll actually close the program out, and then you have to start over. You can just click Acquire a new sample, and then it will take in a new reading, and you can keep on moving forward that way. Alright, so now for the deliverables. For part 1, we have 3 deliverables that we're going to want to go with. First one is a normalized semi-log plot for frequency, and you'll want to set this to a log scale because you'll have a lot of clumped up values on the really low end and then a few stray values on the higher end, and so this will allow you to more evenly space those data points. Same idea for the next plot, except in this case it'll be amplitude. And then the last thing that you'll want to do is fill out this table here, which is also given in the lab manual, where you get the expected measured signal. And so the expected is not just 1000 hertz. It'll be 1000 hertz when the Nyquist criterion is being fulfilled. But then once you get into the lower frequencies, you'll want to use that aliased equation in order to determine what the expectation is. Then you'll want to give the measured signal, so whatever frequency that peak occurs at. Use the leakage equation to determine if you expect there to be leakage, and then give the measured amplitude at that peak. So now we'll move into part 2 with the setup. Here's a little bit more busy, and I'll clean this up a little bit. So here we have this purple region, which is the oscilloscope. So the first step you'll want to do is for each function generator, you'll want to set it up in the same way that you did with part 1, using the oscilloscope to make sure that they are all at the same 5-volt peak-to-peak signal for the frequency that you are given in the lab manual. Important note is that group 2 is the only group that has 3 function generators. Groups 1 and 3 can ignore this wire here. And then this will move into the summing amplifier, which adds these signals together and either passes through the filter or goes directly through. When it goes directly through with the dashed lines, that acts as your control, and then you've got your filtered signal. So you want to actually test both conditions separately, and then you'll measure your information with the DAC. And something to note here is that there is no speaker. The reason why is because it is very difficult to audibly tell the difference between the filtering because our ears work on a logarithmic scale. For the summing amplifier, the basic idea here is that you can combine the different signals from the function generators and it superimposes them on top of one another, basically adding those waveforms together. It can amplify, but that amplification is based upon the resistors used. And so if we have the input resistors set equal to the F resistor, you can see in this equation that each of these will turn to unity. And so then it's just an addition of these signals. All right, so walking through the procedure for part 2, again, we will want to first make sure that each of the function generators are set to the proper frequency and voltage, all set at 5 volts peak to peak with different frequencies. Combine those function generators using the summing amplifier, and then send the output of that amplifier directly into the DAC and gather the DFT information for a control. And then you'll want to construct your filter, which is specific to each group, pass that signal from the amplifier into the DAC, and collect the DFT information for that for comparison. You'll want to make sure that you check that DFT information to make sure your goal is being obtained, which the goals are outlined differently for each group, and you may want to adjust the filter as needed. So group 1, you will be in charge of constructing an anti-aliasing filter, or in other words, a low-pass filter, which is governed by these 2 equations for amplitude and phase shift. And so you're going to be combining 2 signals. One is a 200 hertz signal and one is an 1800 hertz signal. You'll want to be very careful about this because with the aliasing, the 1800 hertz signal at a sampling frequency of 2 kilohertz results in an apparent frequency of 200 hertz. So it's very crucial that you align these frequencies so that when you check the control condition, those 2 peaks overlap perfectly before you move on to testing your filter. And so your goal will be to reduce this aliased 1800 hertz signal down to 20% of its original voltage. And so at your disposal for constructing the filter will be a decade resistance box, which is basically just a fancy variable resistor that you can adjust using these knobs. And the cap ranger is the same idea as the decade resistant box, but for capacitance. So these little knobs will allow you to add in a different capacitance value. For our case, we are just going to simplify this equation by setting the capacitor equal to 0.1 microfarads, which will simplify your calculations. And here is a electronic schematic of your RC circuit. Group 2, you're tasked with constructing an isolation filter, aka a bandpass filter. So you'll notice that the equation is actually a composition of the low pass and high pass equations, basically because you're passing it first through the low pass filter and then moving on to a high pass filter. And a simplification that we make is that the resistance and capacitance are equal, and therefore the time constant that you would calculate is also equal. And so this can simplify both of these equations to what's given here. Since we're dealing with a bandpass filter, we're going to have 3 signals instead of 2, where we want to reduce the 2 outlier signals while maintaining this central signal. In order to run this, you'll want to set the sampling frequency to 7 kilohertz, with n remaining the 1024 with all the other conditions. Now, to simplify your setup, since you're dealing with a little bit more, we are actually providing you with a pre-made filter box. And so based upon where you plug in, you will get either a low-pass filter or a high-pass filter, but the resistance and capacitance is locked in place as 47 kiloohms and 2.2 nanofarad. All right, group 3, you are tasked with constructing a decoupling filter, which in our case is a high-pass filter, which will remove the low 300 hertz signal while maintaining the higher 1539 signal. In your case, you're going to set the sampling frequency to 4 kilohertz, and your goal is to reduce that 300 hertz signal down to 20% of its original amplitude in a similar form to group 1. And again, for your filtering equipment, you'll have the decade resistance box and cap ranger. Now, here is an electronic schematic of what your high-pass filter will look like. And now we'll talk about deliverables. So for part 2, what you'll want to do is you're going to be collecting 2 DFTs, one from the filtered and one from the unfiltered signal, and you're going to want to plot them on the same plot, because this way you can actually see the difference or the reduction that you get from the filtered versus the unfiltered signal. Then you'll want to determine how much reduction are you actually getting with your signal and compare those reductions to what your expectations are for your filter based upon the amplitude equations and your RC circuit. All right, moving into part 3, starting with the setup. This here we see is a little more simplified. Again, I'm going to switch over to an electronic schematic, and we see a lot less going on here. We're going to have a single function generator, again having a 5 volt peak-to-peak signal, but your frequency will now be a variable that you will adjust while you're testing. You will then get both a filtered and unfiltered signal simultaneously being plugged into the oscilloscope, with the unfiltered signal going into channel 1 and acting as your voltage in, and then your filtered signal going through channel 2 and acting as your V out. And just to clarify, you will not be using a DAC or LabVIEW or the speaker for part 3. So the first thing that you'll want to do is to figure out what frequencies you'll be testing at. And so make sure that you complete your pre-lab, which instructs you to create a theoretical Bode plot for your filter, both for amplitude and phase. And so for your phase Bode plot, you will want to use that in determining your maximum and minimum testing frequency. And the reason why is because the oscilloscope has a difficult time reading signals within 5 degrees of your maximum and minimum phase shift. And so you'll use those as your cutoff points. And so this region here will be your effective testing range. Another complication is that when constructing a Bode plot, you want to plot it on a log scale. And so therefore you want to test your frequencies also on a log scale. And so for base 10 log scale frequencies are called decades. And so you'll want to calculate that based upon figuring out what your Fmin and Fmax is, and passing it through this equation here to get a Dmin and Dmax, and use that to calculate your change in your decades just by taking a difference between the two and dividing it by 1 less than the number of samples you plan to measure from. And so for groups 1 and 3, you'll want to have at least 15 samples, but for group 2, you'll want a few more because you'll actually have 2 roll-off regions, so you'll want to characterize your signal more carefully. And so once you've gotten this delta D calculated, you want to iterate those values out and then convert those decade values back into frequencies, and that will give you a list of frequencies to test with. So the next piece here is, now we've got the frequencies we're going to use. Now we hook it up to the oscilloscope and have that one function generator plugged in to channels 1 and 2 based upon filtered or unfiltered, and then push auto in order to make sure that both channels 1 and 2 are activated, you want to click on the measure button and clear, just like before. And also, just like before, you want to select voltage and select the V peak to peak. But now this time you'll want not only channel 1's peak to peak, but channel 2's. So you'll select the blue button next to channel 1, which will then switch it over to channel 2. And then you can go back to voltage and select peak to peak, which will be the peak to peak for channel 2's information. And then you'll want to go to time and select phase 1 to 2. Then you can select the menu on-off button in order to remove that menu. And now you'll be adjusting the frequencies on the function generator according to what you calculated in the last slide. And you'll be recording the V peak to peak for channel 1 and 2, or in other words, V in and V out, as well as the phase shift between the two. As you're adjusting these frequencies, make sure to occasionally adjust the horizontal and vertical scale. My recommendation is as you're checking these signals that you plot this as you go along in order to make sure your results are making sense. All right, finishing it out with the deliverables here. What you're going to want is an amplitude Bode plot of your filter, which should include both theoretical and experimental data. And you'll want to highlight the cutoff frequencies for both, as well as the linear regression of the roll-off regions. And so for group 2, you'll actually have 2 regions to analyze. Make sure whenever you do linear regression, include confidence bands, R-square value, as well as the best fit equation on your plots, which can get a little bit compressed, so make sure you're strategic about your formatting. The second plot you need is a phase Bode plot, again with theoretical and experimental data. But in this case, you'll just need to highlight the cutoff frequencies for each. And then the last item is that you'll want to fill in this table that I'm showing below, which has a slot for the cutoff frequencies and the roll-off for each of the methods. Note that the phase slot is dark, and that's because roll-off does not apply to the phase method, though you can get it for the other two. Alright, that is everything I've got for Lab 2. I hope this video has been helpful and that you have a wonderful day.